Today we're going to talk a little bit about light and telescopes and explore what the universe looks like at various different wavelengths that we can see through astronomical instruments and observations. So what I'm looking at right here is a program called Worldwide Telescope. This is accessible via your web browser, and it is a compendium of pretty much all of the astrophysical data we have on the sky. So it's funded by the American Astronomical Society, and it's designed to be kind of a clearinghouse for all of the astronomical data and all the astronomical images that we have been collecting over the years. Now, one thing you have to realize about astronomy is that astronomers are studying light. The light that reaches us from other stars is the only way we can study the objects in the universe. And because of that, we use telescopes, and telescopes collect that light and then we can analyze it. Through most of human history, that analysis occurred with our eyes in the visible wavelength. It wasn't until the early 1900s that we started recording data in the radio frequencies, which is another form of light at very long wavelengths that tells us more about the universe. In fact, it wasn't even until the latter part of the 1900s, 1980s, 1990s, where we were collecting data across the entire electromagnetic spectrum. Everything from high energy gamma radiation, X-ray radiation, all the way to low energy infrared and radio frequencies, and everything in between. So now we have this huge collection of data, and you can see what the universe looks like from pretty much all parts of the electromagnetic spectrum. So that's why I thought I'd show you today, and this is something you can play around with yourself online. So let's go ahead and start with a constellation that we're familiar with. So this is a constellation, Ursa Major, the Big Dipper. We can see this arc here and these three stars. We've learned before that you can go from the Big Dipper to Polaris, the North Star, so I'm going to do that. Let me just maneuver us around here. And remember, if I follow these two stars, I'll get to Polaris, which is the pole star. Now, constellations are like anything else. You can build a repertoire of constellations that you can find. So you already have the Big Dipper in your repertoire. So let's add another one. That one is going to be the constellation Cassiopeia. And if you go from the Big Dipper across to Polaris and then continue across, you'll hit this W constellation, and that's called Cassiopeia. And Cassiopeia is just right next to the start of the Milky Way galaxy as it starts to cross the sky. So I'm going to go ahead and follow that around here to see the rest of the Milky Way. So if I come down here to the Milky Way, we hit another constellation. This is called Cygnus the Swan. You can see this cross here. And as I come down here, we're going to see the center part of the Milky Way galaxy. And the reason I'm showing you that is because I want to see what the Milky Way galaxy looks like in all these different frequencies of light. So this is the optical survey of the night sky, and we can see that the Milky Way glows in some respects, and it's also very dark in some respects, and that's because there's dust and gas that's blocking the optical light that's coming from the Milky Way galaxy. So what we're going to do here is we're going to overlay this with some other telescopic observations of the night sky. So I'm going to go ahead and change my view here really quickly to the galactic plane mode, just so I can see the galaxy in its entirety. And then I'm going to come back and look at a part of this called All Sky Surveys. So if I click on All Sky Surveys, you can see I have a collection of different instruments that have taken data all the way from the low frequency radio frequencies all the way up to very, very high frequencies. Those are going to basically be high energy on one side and very, very low energy on the other. So I'm going to start with things you might be familiar with, such as infrared. So this is our optical wavelength. Let's go ahead and look at the dust map, which is the glow of the dust in the Milky Way that's due to the infrared. So if I click on that, you can see it instantly changes, and we see this plate, this thin disk of material that is emitting warm radiation from warm dust, and you can see that that stretches all the way around in the Milky Way. So that's really showing us the distribution of dusty material in our galaxy. If I look at a little bit further into the infrared, we can see that's even more extreme. And in fact, you can start to see that there's kind of a central part to this Milky Way galaxy. It's brighter in this direction than off to the edges. And then if I keep looking at the Milky Way in the infrared, these are now getting to longer and longer wavelength, or I should say shorter and shorter wavelength infrared. You can see that that disk still seems to predominate. And in fact, if I look at this is now closer to the optical region. We're getting close to optical here. You can see this starts to look a little bit more like the optical part of the spectrum that we're used to. So let's go back to the what we see with our eye. That gives you an idea of what you can see when you can peer through the material that's blocking the Milky Way and actually see the shape of the Milky Way itself. So now let's take a moment and go from the infrared to the very, very, very high energy realm and look at what it looks like in the high energy. This is the gamma radiation from the entire. Okay, now let's go ahead and look at the high energy, which is the gamma radiation from the galaxy. If I click on that, you'll notice that there's still this kind of plate looking structure to the galaxy that's telling us that our galaxy is a disk. But we also see in high energy gamma radiation, we see some what are called point sources. Those are because very, very, very high mass stars emit a lot of high energy radiation. So you can see those point sources that we weren't really seeing in the dust map. Right? So this is telling us, again, showing us some of the structure of the Milky Way, but it's also showing us a different perspective of the Milky Way galaxy. Now, if we look at the radio frequencies, I think last time, or one of the last times I showed you what the universe looks like as we expand out, we get to what's known as the cosmic microwave background. Well, what does that look like on the sky? Well, we can overlay that onto our galaxy here, and this is what the cosmic microwave background looks like. This is an instrument called WMAP, and we have some higher resolution images from a thing called Planck. And this is what the sky looks like at radio frequencies that peak at the cosmic microwave background region. This is basically the afterglow of the Big Bang that you're looking at right here. Pretty remarkable that we can observe this, and it's nearly uniform in all directions. There are fluctuations, but these fluctuations are relatively small. But you don't see any structure of the galaxy or anything like that. And the reason for that is because we're looking at the glow that's left over from the origin of the universe. Now I can put the Milky Way back on so you can see what that looks like. Let's get back to our galaxy, center part of the galaxy. There it is. Back to the optical spectrum. So that's what it looks like. Radio frequencies, it's what it looks like at high energy gamma radiation frequencies, and it's what it looks like in mid-range frequencies, optical and infrared. And there's a whole bunch of other interesting things that you can explore with this, but it gives you an idea of what sort of astrophysical observations we've been taking in the modern era. And there are numerous telescopes that are in orbit around the Earth or even in orbit around the Sun that are taking data all of the time. And if you want to play around with this, this is a really cool program. For example, you can find pictures of galaxies in some of these all-sky surveys and then even zoom in on them so you can see what that would look like if you had a really nice telescope. Some of these all-sky surveys are really spectacular. So it's a way of exploring the night sky and be able to use some of the best data that we have available. Down in the lower left-hand corner, there's even places where you can look at panorams of different planets. So this is the moon, and these were panoramic images taken from the lunar orbiter or the lunar lander, and you can see the instruments laid out there on the lunar surface. This is the Apollo 12 landing site. I can go visit Mars. The current mission on Mars is, let's see here, what do they have? They have, looks like they don't have the current mission, but they do have Opportunity. I can go look at that one, look at pictures of Mars, and a bunch of other stuff. They even have planets. You can look and see what the surfaces of the planets look like. And again, this is all real data from NASA's various instruments that have gone around the solar system and looked out into space from Earth and elsewhere. So the other thing I want to do today, because this is an introduction to light and telescopes, is to take a little bit look at different types of telescopes in case you are interested in purchasing one. I'll put this link in the comments section so that you can find it again. But Sky and Telescope magazine, which is a great magazine if you're interested in learning how to observe the night sky, has a great how to choose a telescope guide for beginners. One of the things I will tell you about observing is that you need nothing more than your two eyes to see a lot of really cool stuff. You can just lay out in the grass, look up at the night sky, learn your constellations, and see the Milky Way and do some interesting things. In fact, the best tool that you can have, if you have a pair of binoculars, that's the first place you want to start, because you can lay down in the grass and just look up in the sky with a pair of binoculars, and you'll be able to see star clusters, you'll be able to see some galaxies, you'll be able to see structure in the Milky Way, you'll be able to see craters on the moon, the moons of Jupiter, a whole bunch of stuff. However, if you really get into this and you want to look at some more sophisticated instruments, this Sky and Telescope magazine guide is a great thing to look at for finding out how to use telescopes and how to buy telescopes. You can go ahead and read through this. I'm just going to zoom down here to the different types of telescopes. So there are basically two types. There's a refractor, which uses a lens to focus the light, or a mirror, which is a curved mirror on a reflecting telescope that is also used to focus the light. The advantages to a reflector telescope is that they can be much bigger for the same weight, and all the weight is located at the bottom, so they're a little bit easier to build and easier to build larger. And the biggest benefit that you can get from a telescope is that it allows your eyes to collect more light. So the bigger the telescope, the better. You're not really after magnification, you're just after how much light can the telescope gather. So if you can find a large telescope, that's going to be better than a smaller telescope more often than not. And in fact, you can even build your own telescopes. They've got some really interesting kits, especially for these types of telescopes called Dobsonians, which lets you build, they come with the optics and the tube, and you put them together and they make a nice telescope for looking, panning around the night sky and seeing some interesting stuff. So take a minute to look at that if you're interested in possibly purchasing a telescope. My biggest tip again is to start with binoculars, because if you have trouble finding things in the night sky, you're less likely to use the telescope that you do buy. So it's better to start with something that's easy to use rather than something that is really good but hard to use. And if you start with a nice pair of binoculars, even if you just want to go spend $80 or $100 on a reasonable pair of field binoculars, that will get you a long way to seeing some very cool stuff. You'll have an instrument that's way more sophisticated than what Galileo had, and Galileo could see the phases of Venus, the moons of Jupiter, the craters on the moon. Okay, so this week again you're going to be looking at how astronomers use light and how we use telescopes to collect that light, and I will see you next time.